My Mathematics Association, great pride and pleasure in welcoming you all for the second session of the day. Earlier in the first session, we had Professor Berndt talking to us on the topic Ramanujan and the very strange sum. Sri Srinivasa Ramanujan's work are always interesting for mathematicians. Now, we are very much eager to hear yet another aspiring work of Sri Srinivasa Ramanujan from our eminent speaker, Professor Bruce Berndt, on the topic Ramanujan, a century of inspiration. Now, I request Professor R. Shivaraman, founder, Pi Mathematics Association, to introduce our distinguished speaker of this session. Please, sir.
Thank you, madam. Uh, Pi Mathematics Association take great privilege to invite Professor Bruce Berndt for this lecture, and we are very grateful for him to accept this one. A very short introduction, because when I saw the full accomplishment, we could write a whole thesis on it. That much achievement that he had made in his lifetime, and I could proudly say that he was born on one day before the World Pi Day. So that's a clue for people to guess. One day before the World Pi Day, 81 years ago. So he was 81 now. So even in this ripe old age, he could do many active research. That's one of the characteristics of Professor Bruce Berndt. He was very active in his research even at 81 years. And he did his MS and PhD at the University of Wisconsin. MS in the year 1963 and PhD in the year 1966. Uh, and then he was professor at University of Illinois, Urbana-Champaign from the during the years 1975 to 2019, and in the year 2019 he was emeritus professor there at the same university till now, and he was visiting professors for about 1 to 6 weeks at 11 universities globally. I will list a few of them: University of Oslo, Tel Aviv University, National University of Singapore, Korea Institute of Advanced Study, and many more. I mean, the other things I haven't listed out. And they had got 8 primary and very special awards and honors for his work. I'm again listing few of them, not everything. Allendorfer Award and Ford Award from Mathematical Association of America. He got Allendorfer Award in the year 1979 and Ford Award in the year 1994. Of course, the most prestigious Steele Prize for Mathematical Exposition from American Mathematical Society, AMS, which is one of the most premier mathematical society in the whole world, in the year 1996. And he got honorary doctorate award from Sastra University in 2012. I hope he could never forget that occasion, because that is the 125th birth year anniversary of Srinivas Ramanujan, when he, Professor George Andrews both came, and I hope both got award, and they took a pride picture after taking the award. So that's a great news actually. Both of them were given honorary doctorate awards for their excellent work in editing Ramanujan's notebooks. And he was editor for 10 important journals, and he was especially he was founding editor for the International Journal of Number Theory from 2004 till date. He was associate editor at Journal of Mathematical Analysis and Applications, Advances in Applied Mathematics, the Ramanujan Journal, Mathematics Student, which is published by Indian Mathematical Society, and much more. As I told you, the list goes very long. So we want a listen process lecture. So I'm just listing out whichever is very interesting from the whole list that he has given. And he had been in professional committees and other prize committees of Mathematical Association of America and American Mathematical Society, MAA and AMS. And he has guided nearly 40 PhD students so far, almost 40, I think 39 or something. Maybe. And I know that a couple of them are from India, as far as I knew. One is Atul Dishik, where he came at that time when I met him for his marriage. He came here, and Amita Malik. I hope that is also in India. And As of November 17, 2020, he had published 246 original research papers, most of them related to number theory, and published 15 books, and he has edited 15 books, and he has supervised 11 postdoctorates, and he had been interviewed in National Public Radio, Voice of America, the Canadian Science Program, Quicks and Quarks, and of course in Indian famous magazine Frontline. But these things are very little compared to his original work and contribution. No words are sufficient to introduce him or mention about his accomplishment. But still, it is for the sake of those who had been attending new now. This introduction is necessary, but people like me and others in working in number theory, Bruce Berndt name itself is enough for us. So we are very happy to be with you, sir, today, and we are very pleased and privileged. Thank you.
Well, thank you very much for the introduction. Since you mentioned my birth date, let me add a couple words to this. My father was born on March 11th, 3 days before Pi Day. And as you indicated, I was born on March 13th, 1 day before Pi Day. My daughter, whom you might have seen a few moments ago, was born on Pi Day. So we gradually converged in our family to a birth on Pi Day. So before beginning, I would like to express our thoughts and prayers to all those families who have lost loved ones, who have suffered serious illness, and who have encountered economic hardship due to COVID-19. So here's an outline of my lecture. I'll say a few words about the life of Ramanujan, talk about the history of Ramanujan's notebooks and the history of the lost notebook. If you'll permit me, I'll say a few words about how I became involved with Ramanujan's work. So that's the fourth title here, my 46 years working with Ramanujan. And then I'll also give examples from Ramanujan's notebooks and lost notebook. So I always begin a lecture on Ramanujan's work with his passport photo. Of the 4 photographs that exist of Ramanujan, this is the most famous. It was taken prior to his return to India in 1919. He was very sick at the time, and he was unable to go to the photographer to have his passport picture taken. So you can see here, he is in his bathrobe and pajamas in this photograph. So let me begin with just a very brief account of Ramanujan's life. So most of you will be familiar with this. I was born on December 22nd, 1887 in Baroda, the town where his grandparents lived. And then shortly thereafter, his mother returned to Kumbakonam with her newborn son. And in Kumbakonam, Ramanujan lived for most of his life. He started to record his notes, his results in notebooks, we think around at the age of 15 or 16. So let me, before I go that, just mention that I had the privilege of attending Ramanujan's home in 1987 before it was turned into a museum. So this is one of the greatest thrills of my entire life. It was really a privilege to see the home in its original state before it was turned into a museum. So when I visited the home, the only indication that this was the home of India's greatest mathematician is this picture that the family living in the home had of Ramanujan that they had cut out of a newspaper. Otherwise, there was no indication that this was Ramanujan's home. Okay, as I started to say, Ramanujan worked on a slate, and he would then take the results from his slate and then put them in notebooks. So this actually is the original slate. It's now in the family of S. Iyer. And this is my favorite picture of myself holding this slate. So almost all students when Ramanujan was growing up worked on a slate. Paper was expensive, so Ramanujan again worked on his slate and then would record only the results from his slate in notebooks. So let me just briefly discuss the reasons that have been suggested for the lack of proofs in Ramanujan's notebooks. So it's often been said that Ramanujan was greatly influenced by Carr's book, which gives a succession of over 4,000 formulas with few proofs. So we think that Ramanujan borrowed Carr's book from the local government college library at about the age of 15. Carr was a tutor. He made his living by tutoring students for the Tripos exams in Cambridge and in London. So because there were very few proofs in this book, it has been suggested that this served as a model for Ramanujan's recording results in notebooks. And as I mentioned before, paper was expensive. He just worked from his slate as other students did at the time. He could only afford to record his results and not the proofs in notebooks. And then thirdly, his theorems were really only a personal account of his discoveries. I'm sure that Ramanujan felt there was no need really to record the proofs. If someone asked him how to derive a certain formula, I'm sure he could actually do so. Now, some have suggested, excuse me, that he didn't have proofs, that he derived the results from an unexplainable intuitive process. And then also it's been suggested that he was following an age-old custom in India. So perhaps all of these suggestions or reasons have some merit. When I first started to work on Ramanujan's theorems in these notebooks, I thought maybe item 1 here was the main influence, but in recent years, I think that item 3 is the main reason. I'm sure that if people again ask him, how do you prove these formulas, he would be able to give his arguments. So Ramanujan went to the government college of Kumbakonam for 1 year, but then didn't pass his exams at the end of 1 year, and he had to leave the government college. He lost his scholarship and couldn't afford to continue his education. So eventually he moved to Madras in 1910, and 2 years later, in 1912, he began work in the Madras Port Trust office as a clerk. And he was hired in the accounts department by S. Narayana Iyer. So this is a photograph of S. Narayana Iyer. He was probably one of the best mathematicians in India at that time. So he and Sir Francis Spring, the chairman of the Madras Port Trust, encouraged Ramanujan to write English mathematicians about his work. He wrote 2 at Cambridge, Baker and Hobson, and he wrote Professor M.J.M. Hill in London. So Hill responded, but it was clear from the letter that exists, he didn't really understand what Ramanujan was writing. And Baker and Hobson evidently never replied to Ramanujan's work or letters. So then finally, he wrote G.H. Hardy, who encouraged Ramanujan to come to England. And then early in 1914, he did accept Hardy's invitation and went to England. So here is probably the most famous photograph of Hardy. So in the first letter that Ramanujan actually wrote to Hardy, I would like to indicate just a few of the results in this letter. So here Ramanujan says 1, 2, 4, 5, 8, 9, 10, 13, 16, 17, 18 are numbers which are either themselves squares or can be expressed as the sum of 2 squares. And then the number of such numbers greater than A and less than B is given by this formula, plus an error term. He gives the decimal expansion of the constant in front of the integral. And he says that theta of x is very small. And he says that k and theta of x have been exactly found, though complicated. So note there is a slight misprint here. You should have theta of b instead of theta of x here. So this is really a remarkable theorem. It actually was discovered by Landau at about the same time. But it's really remarkable because Landau had, the entire century of European mathematics behind him or to learn from, but Ramanujan had nothing to learn from. And the fact that he made this leap into this theorem is really a remarkable feat. And G.N. Watson also in his writings expressed amazement that Ramanujan was able to reach such a theorem. And I'll come back to this later in my talk. So there are many integrals that Ramanujan gave in his first letter to Hardy, which contained over 60 results. So here is one where we have a quotient of two infinite products, and the integral is expressed in terms of gamma functions. And this is what I think is one of the most interesting results in Ramanujan's first letter. He defines this function phi of n in this way, and then establishes sort of a reciprocity theorem for phi. So in the theory of theta functions and modular forms, we usually have relations between the variable and then the function with the reciprocal of the variable. So we have that sort of relation here. So this is a very beautiful formula giving this type of reciprocal relation involving its companion result or companion integral involving the sign. So he says that phi of n is a complicated function, and then he gives several values. So I've never been able to figure out any general formula here. Note that two of them actually involve pi and the others don't. So I have no criterion. I've never been able to figure out any criterion for when the evaluations are algebraic numbers, as you see here, or involving pi. So I've long felt that this is a result from the notebooks that really should be studied further. But Ramanujan wrote a second letter to Hardy before accepting Hardy's invitation to come to Cambridge. So I'll not give any results from that letter, but just go now to his stay at Cambridge. So let me quote from this letter that he wrote to a friend, Vinayaka Rao, in Madras on March 24th, 1915. I was not well till the beginning of the term owing to the weather, and consequently I couldn't publish anything for about 5 months. So already you see that just after 1 year in England, he was not feeling well. So generally, we know that Ramanujan began to be a patient in nursing homes in mid-1917, but here, as you can see, he seemed to be in poor health long before he went into nursing homes. And here we see in a letter that Hardy wrote to Mittag Leffler, he mentioned, "You will be sorry to hear that Ramanujan is seriously ill and that we are very much alarmed about him." So in 1918, he was elected as a fellow of the Royal Society. I've separated the members of the Royal Society who signed the election papers into two categories. The ones in italics were not present, but they had signed the page approving his election to the Royal Society. And note the names of Hobson and Baker. So these were two mathematicians, as I remarked earlier, that Ramanujan wrote before he wrote to Hardy. So evidently their thoughts of Ramanujan greatly improved after Ramanujan arrived in England. So in this letter of Hardy to Francis Dewsbury, the registrar at the University of Madras in November of 1918, indicates that, excuse me, Ramanujan's health seemed to have gotten better. There is at last, I am profoundly glad to say, a quite definite change for the better. I think we may now hope that he has turned the corner and is on his road to a real recovery. His temperature has ceased to be irregular and he has gained nearly a stone in weight. The consensus of medical opinion is that he had been suffering from some obscure and only partially diagnosed source of blood poisoning, which is now dried up. It appears that these prognoses that doctors made of Ramanujan were incorrect. So Ramanujan returned to India in 1919. After he returned, he wrote to Hardy only once, and I'll come back to that letter later in my lecture. And after he died, the suggestions were made that his published papers not only be brought together for publication, but also his notebooks. So his published papers weren't collected until 1927, but the London Mathematical Society was evidently in poor financial condition at that time, and so they didn't publish his notebooks. So let me just have you look at this title page from the collected papers for just a few seconds. So let me ask if you see anything unusual about this title page. I'll give you a few seconds before I tell you what is unusual. Okay, note that B.M. Wilson's name is in larger letters than those of Hardy and P.V. Seshu Iyer. P.V. Seshu Iyer was Ramanujan's mathematics teacher in the 1 year that Ramanujan attended college in Kumbakonam. So Hardy mentioned later in his writings that, in fact, Wilson really did all the work in putting the papers together for publication. So evidently Hardy felt since he really did all the work, Wilson's name should be in slightly larger letters than himself and P.V. Seshu Iyer. Yeah. Okay, so let me just in detail now give a little bit more history of Ramanujan's notebooks. So I emphasize that he began writing things in his notebooks about the time he was 15 or 16 when he entered the government college in Kumbakonam. And he recorded results in his notebooks until 1914 when he went to England. So in other words, over a period of about 10 years now. So from a letter that Ramanujan wrote to another friend in 1915, he says, I am doing my work very slowly. My notebook is sleeping in a corner for these 4 or 5 months. I am publishing only my present researches as I have not proved the results in my notebook rigorously. So 2 things I want to note. There is really only one notebook at this time. And it appears from this letter that Ramanujan was not recording any further results in his notebook. He was concentrating on publishing results in papers. Yeah. So when Ramanujan returned to India, he actually left his first notebook with Hardy. But at that time, he had really 3 notebooks. So sometime probably late in Ramanujan's stay in England, he formed a second notebook, which is an enlarged edition of the first. Yeah. And then he had a third notebook, which we think was probably composed before he returned, we're not 100% sure. The third notebook just has 33 pages. So let me just describe a little bit more about how many pages were in the first and second notebooks. So as I mentioned, the second notebook is an enlarged edition of the first, but in my working through the notebooks over a period of several years, I found about 200 results altogether in the first notebook that were not in the second notebook. The second notebook has 21 chapters, fairly well organized into 254 pages. And then these are followed by about 100 pages of unorganized material. The 33 pages in the third notebook are unorganized. And in the first notebook, most of the results are unorganized as well. Yeah. So again, we think that the second notebook was written in about 1918, maybe in the year before he returned. I'm quite sure that it was not written after he returned to India. In particular, since the second notebook is an enlarged edition of the first, really he would have had the first notebook with him as he was composing the second notebook. Yeah. So in a letter that Francis Dewsbury, the registrar at the University of Madras, sent to Hardy in August of 1923, he says the following: I have now seen your letter dated 19th of November, 1921 to Mr. K. Ananga Rao. Ananda Rao was actually a student of Hardy, and his stay in England coincided almost exactly with the stay of Ramanujan in England. He says, in which you have stated that one of the late Mr. Ramanujan's notebooks is with you. I shall be glad if you will return the original notebook when you have extracted from it selected material for printing in the memorial volume, that is, the collected papers. So it appears that Francis Dewsbury thought that Hardy had a second notebook and that he had the first notebook, but in fact it was the other way around. Francis Dewsbury had the second notebook that was given to the University of Madras after Ramanujan's death, and Hardy actually had the first notebook. So a copy of the notebooks, the second notebook, was actually sent to Hardy. The first notebook was returned to Hardy in 1924, and then a handwritten copy of the first notebook was also sent to Hardy. And we think the third notebook was copied and also sent to Hardy as well. So as I mentioned, the notebooks were not published with Ramanujan's collected papers. So in 1928, B.M. Wilson and Jan Watson began to edit Ramanujan's notebooks. So Wilson worked on this project for 5 years, but then unfortunately he incurred an infection when he was in the hospital for a rather routine surgery, and he died from the infection. And Watson worked on editing the notebooks for about 10 years and then eventually tired and didn't finish the editing by any means. No. So they divided the material, concentrating in the second notebook. So if I recall correctly, Wilson was to edit the first 14 or 15 chapters, and then Watson the remainder of the chapters. Yeah. So the notebooks are at the University of Madras. So I took this picture of the notebooks, I think in 1987. So unfortunately, cameras were not as good as they are now. And one of my chief desires, is to return to Chennai and take a better picture of these notebooks. So they were not published until 1957. And this publication did not include any of the editing of Watson and Wilson. These are just a photographic reproduction of the notebooks. So this is my copy of the notebooks. I took this picture a couple years ago. I put up an Indian tapestry behind the notebooks for this picture. So I got this in one of my, it's a beautiful tapestry that I received in one of my 11 trips to India. And then in 1912, a new edition of the notebooks was published. This is my copy of the new edition. So the writing is clear in the new edition, but actually I didn't really have many problems reading the first edition. There are a few places where it was difficult to read Ramanujan's writing, but generally in the first copy in 1957, it's quite easy to read what Ramanujan was saying. So I began working on editing the notebooks, that is, proving the results in the notebooks in 1974. And I'll say a few more words about that when I indicate in a few minutes how I became involved in editing the notebooks. Okay, so as was indicated in the introduction, I was a graduate student at the University of Wisconsin, and I had never taken any course in number theory until the spring semester of my third year at Wisconsin, when I took a course from Rod Smart in modular forms. So this was the first course I had ever taken, and I enjoyed the course so much that I asked Smart to be my advisor. And then in the following fall semester, so this would be the fall semester of my fourth year at Wisconsin, I took a course in modular forms with applications to number theory. So this was taught by Marvin Knopp, and it was here for the first time that I learned about Ramanujan. In particular, in this course, I learned about the asymptotic formula for the partition function, famous asymptotic formula of Ramanujan and Hardy. And then I also learned about Ramanujan's congruences for the partition function. Although I didn't take any courses from Richard Askey, since I was a graduate student at the University of Wisconsin, he has been a mentor to my work. He has commented on many of the results that I was proving or results that I hadn't proved. And I owe a lot to Dick Askey for all the help he has given me since I was a graduate student. He became interested in my work when I wrote my thesis, because in my thesis I had a lot of Bessel functions. Askey was the world's leading expert in special functions for many years. And this is how Askey became interested in my work, and I became interested in his work. So unfortunately, Askey died a year ago this past September. So after I received my PhD, I went to the University of Glasgow for 1 year, and there my mentor was Robert Rankin. Rankin was actually the last PhD student of Hardy. So one day I was in Rankin's office, and we started talking about Ramanujan. I don't remember exactly how we got talking about Ramanujan, and I unfortunately don't remember very much about our conversation. But what I do remember is that he told me about Ramanujan's notebooks for the first time. He had in his office the Tata Institute's publication from 1957, and he said to me, "I'll be glad to loan you these notebooks." And I told him that I wasn't interested. Yeah. A very unfortunate reply to his kind invitation. So in January of 1967, during my first and only year in Glasgow, I received a letter from Paul Bateman, the head of the mathematics department at the University of Illinois, offering me an assistant professorship. To tell you the truth, I had applied at Illinois only at the suggestion of Marvin Knopp, who was a former PhD student of Bateman. I was really not interested in teaching at a large university. I had done my undergraduate work at a small liberal arts college and thought I would return to some small liberal arts college for my career. But at any rate, I decided to accept Bateman's invitation, and I intended only to stay there a few years. But as was indicated in my introduction, I stayed there my entire career, and I taught actually for 52 years at the University of Illinois. So Bateman is a well-known analytic number theorist as head of the department, and often received requests to referee papers. So in my third year there, Bateman asked me to referee 2 papers of Emil Grosswald. So I did that, and these are the 2 papers that Grosswald wrote and I refereed. So this is the first time that I actually ever read about any of Ramanujan's results. Here is a photograph of Grosswald. And let me just tell you about one formula that Grosswald proved from the notebooks. So this is a very nice symmetric formula involving the Riemann zeta function. So alpha and beta are positive numbers such that their product is pi squared, n's a positive integer. So we have this very nice relation involving this sum in the zeta function at alpha, and then here it is at beta. And then on the right-hand side, we have this finite sum involving Bernoulli numbers. If you let alpha and beta to be pi and replace n by 2n plus 1, then we have this formula for zeta 4n plus 3. This actually was due to the Czech mathematician Larkin in 1901. I always found this a very beautiful identity. So why do I find it so beautiful? Well, most of you know that zeta of 2n is a rational multiple of pi to the 2n. And that rational multiple involves a Bernoulli number. So here we see that zeta of 4n plus 3 is a rational multiple of pi to the 4n plus 3, but not quite. There's, so to speak, an error term. Well, of course, it's not really an error term. It would be an error if we didn't include this sum in the formula. So this is a very rapidly convergent series. So I say that zeta 4n plus 3 is almost a rational multiple of pi to the 4n plus 3. So please realize I'm speaking very loosely here. When I say almost, it's not really in any mathematical sense. So these formulas are actually from chapter 14 in Ramanujan's second notebook. And here is the page where the formulas actually appear. So I went to the Institute for Advanced Study in 1973 for my first sabbatical. And while I was there, I suddenly realized that these formulas that Grosswald had proved, I could also prove by using some results I was deriving about Eisenstein series. So I did that. And then I went home and I kept working on ideas involving what I was doing at the Institute. But I didn't really look seriously at Ramanujan's notebooks until 1977, when the semester ended at the University of Illinois. So I said to myself in May of 1977, let's try to prove all the results in Ramanujan's notebooks. Well, I really started off by only looking at chapter 14, the chapter in which the formulas of Grosswald were proved. So I thought, so I worked on this chapter. It contains 87 results. And I worked on this for over a year. And then George Andrews visited the University of Illinois and told me that the notes that Wilson and Watson had accumulated in their efforts to edit the notebooks we're at the Wren Library at Trinity College in Cambridge. So I thought that if I sent for these notes, maybe I could edit further chapters. So I got a copy of these notes. Their notes were very helpful. So then I just worked on editing Ramanujan's notebooks for over 20 years. And finally, in 1999, I completed my results, my work on the notebooks. And as you can see here from the picture I took just a few days ago, I wrote 5 volumes on Ramanujan's notebooks. So I'd like to acknowledge that I had a lot of help from Watson and Wilson's notes, and I also had a lot of help from my graduate students during this period. In particular, my first graduate student is Ron Evans, and he proved some very difficult formulas from the notebooks. So let me just give you a few topics from Ramanujan's notebooks. So there are a lot of results on Q series and theta functions in the notebooks. So let me define AQ sub n as the product of 1 minus AQ to the k running from 0 to n minus 1. And if Q and m in modulus is less than 1, we can let n tend to infinity. So this is our definition of AQ sub infinity. So Q is usually or often not changed in discussions. So we sometimes then leave off the Q and just write A sub n in this way. So there's an enormous amount of work on theta functions in Ramanujan's notebooks. So here is Ramanujan's definition of a theta function. This is not the standard definition, but Ramanujan liked this definition for several reasons. In particular, it's symmetric in A and B. In particular, if you replace n by minus n, you get the same thing with the exponents of A and B reversed. So f of AB is f of BA. So for many purposes, this is not a good definition of a theta function, but for Ramanujan's purposes, this is the best definition of a theta function. So the results that he proved throughout the notebooks and Lost Notebook are better proved and may not be able to be proved using the old definition or the definition of Jacobi, for example. So this is the Jacobi triple product identity representation of the theta function. And these are the 3 most useful special cases then of f of AB. So this is probably the most well-known theta function. So here I've put together the positive and negative index terms. And here we have the triangular numbers, and here we have the pentagonal numbers. So this is a very famous pentagonal number theorem. So I might say that Ramanujan actually never used this notation. He would always just write out the first few terms of a Q product, and he would also always just write out the first few terms of an infinite series. And as I emphasized, he did not use any of the standard notation for theta functions. So theta functions are part of the theory of elliptic functions, and a number of his results can be put under the umbrella of elliptic functions. But again, he didn't use any of the standard notation for elliptic functions. So I'm going to make a definition, which is maybe a little bit complicated, a couple of definitions, but I want to emphasize one major thrust of Ramanujan's work. So this is the complete elliptic integral of the first kind. And the k which appears here is called the modulus. So k is between 0 and 1. And as I indicate at the bottom of this transparency, the complementary modulus k prime is the square root of 1 minus k squared. So if you take the integral and expand it in a binomial series, then you easily get this. And here I'm using the rising factorial notation. Now, this is not the Q product notation that I gave earlier, or sometimes called the shifted factorial. And if you're familiar with hypergeometric functions, this is actually a hypergeometric function. So now this seems to be a complicated definition, but I'll explain this and indicate why I'm giving this. So here there are 4 complete elliptic integrals of the first kind associated with these 4 moduli. So we suppose that we have some relation between these integrals of this type, and n is a positive integer. Then a modular equation of degree n is a relation between the moduli k and l, which you get from this equality. So in other words, if you have some equality here involving these moduli, then this implies some relation between the k prime, l, and l prime. So Ramanujan uses this notation. He lets alpha to be k squared and beta to be l squared. And he actually prefers not this definition, but this definition of a modular equation. So remember that on the previous slide, I showed that elliptic integrals can be represented in terms of hypergeometric functions. So Ramanujan loved to derive modular equations, and in his notebooks, there are well over 100 modular equations. So I've just given 3 examples here, modular equations of degree 3, 5, and 7. And Ramanujan actually has several modular equations of some of the degrees. In particular, the low degrees. So if you note the symmetry in these modular equations, and Ramanujan loved symmetry. If he could state a theorem involving symmetry of the variables, for example, he would always state it in this way. Note that the modular equations are different, and in fact, no 2 modular equations of a prime degree are the same. So if one has a modular equation of degree, say, 37 or 31, these modular equations will not be repeated for any other degree. In particular, these modular equations of degree 3, 5, and 7, they won't appear for any other degree. So let me just give you a summary of some of the topics that one can find in the first notebook and the second notebook. There are lots of identities involving infinite series, many results involving theta functions and elliptic functions. In fact, I would say that these 2 are the primary subjects of the notebooks. There's a lot of work involving hypergeometric series and Q series, basic hypergeometric series. So this is another name for Q series, but for a basic hypergeometric series, we assume there is at least one product summand that is a Q product summand. So theta functions are also considered part of the theory of Q series. And then there are lots of results involving number theory. So for example, that result that I stated from Ramanujan's first letter to Hardy, one can find in the notebooks. So now let me go to the lost notebook. So I think this these words are very appropriate through long lapse of time. So that's the time it took from Ramanujan's notebooks that were written, or the lost notebook that was written in about 1920, to the time that George Andrews discovered it. This knowledge was lost. It's not quite lost, as I'll indicate. But now, as you are devoted to the truth that you and my interpretation is George Andrews, I will reveal the supreme secret, namely what I reinterpret as the lost notebook. So George Andrews visited Cambridge in the spring of 1976 And Lucy Slater, who you see in this picture, encouraged Andrews to go to the Wren Library at Cambridge and he might look through the papers of the late G.N. Watson. So here's a picture of Andrews and Lucy Slater. These are his daughters, Amy and Katie. Amy has just written a beautiful book for children on Ramanujan. So I highly recommend this. It was just published about 5 or 6 months ago. So while Andrews was examining the pages for Watson's work, he found 138 pages in Ramanujan's handwriting, and he called this Ramanujan's lost notebook in view of the fame of the earlier notebooks. So Andrews was the perfect person, so to speak, to find this work of Ramanujan. He was familiar with Ramanujan's last letter that Ramanujan wrote to Hardy after he returned from England. And Andrews had also written his thesis on Ramanujan's work. So he was familiar with theta functions and Mach theta functions. He was familiar with Ramanujan's handwriting. So he knew immediately that this pile of 138 pages was from Ramanujan's work, and it was also from the last year of Ramanujan's life. So I'm just indicating here 2 pages, so you can see that, again, there are no proofs at all, and the theorems are compact, very close together. Here is a page which is very difficult to read. Probably the piece of paper was a very thin parchment-like piece of paper, and so when the photographer later photographed this page, he or she was really photographing 2 pages, that is the page and the reverse page at the same time. So the big question is, how did this manuscript of Ramanujan actually reach Trinity College Library? Well, I think we can actually put together the history. So let me return to Francis Dewsbury, the registrar at the University of Madras. He actually wrote Hardy twice, and his his letters were written on August 23rd and August 30th. He says, I have the honor to advise dispatch today to your address for registered and insured parcel post of the 4 manuscript notebooks referred to in my letter here. Okay, so this was then a copy. These were the 2nd and 3rd notebooks. Or I should say a copy of the 2nd and 3rd notebooks. Then I also forward a packet of miscellaneous papers which have not been copied, as it is left to you to decide whether any or all of them should find a place in the proposed memorial volume, that is, the collected papers. Kindly preserve them for ultimate return to this office. Well, evidently, Hardy never returned any of these miscellaneous papers. So almost certainly, this packet of papers included Ramanujan's lost notebook, or what we now call Ramanujan's lost notebook. So it is very unfortunate that Dewsbury did not make a list of all of the papers that he was sending to Hardy, which is natural because he expected Hardy to return them. And then Hardy never made a list of the materials as well. So this again is really unfortunate because some of the papers might have been lost, but we don't know about them. So sometime Hardy gave Watson these papers. We don't know exactly when he did. Watson wrote not only papers on Ramanujan's earlier notebooks and also on results from Ramanujan's first 2 letters to Hardy, but he also worked on the lost notebook, or the last letter to Hardy. So in a paper that he wrote in 1936, he said, It's strange that Ramanujan didn't discover these two third-order Mach theta functions. Well, if he had the lost notebook at that time, he would have seen that indeed Ramanujan had discovered these two third-order Mach theta functions. So it would indicate that in 1936, Hardy had not passed on to Watson these papers that were sent to him in 1923. But it could be that he had these papers because the results were so compactly written and maybe hard to read. Possibly he just didn't devote much attention to deciphering and proving the results in this set of papers. So sometime between the late 1930s and 1947, when Hardy died, Hardy must have passed on all these papers to Watson. So Watson, in particular, wrote a paper on the final problem, an account of the Mach theta functions. That is a paper arising from the last letter of Ramanujan. So he chose this title, The Final Problem, because of a very famous story that Sir Arthur Conan Doyle wrote on Sherlock Holmes. This was actually the last of 24 Sherlock Holmes stories, which became quite famous. And one more reason why Watson chose this title for his paper, Dr. Watson was Sherlock Holmes' sidekick during all of these stories. So he had sort of two reasons for sort of this parody and naming his paper The Final Problem, an account of the Mach theta functions. Yeah. Well, Watson was a professor of pure mathematics at Birmingham University for his entire career. And when he retired, Robert Rankin was named the successor for his chair. Yeah. And then later, Rankin became the head of the mathematics department at the University of Glasgow. So Watson died in 1965, and Rankin made a visit down to Birmingham and to visit his Watson's widow, Mrs. Watson. And they discussed what they should do with all the papers that Watson had left behind. Yeah. So let me just indicate, well, let me go back here to Rankin. So in the discussions that he had with Mrs. Watson, they decided that what Rankin should do is to sort through all the papers, and those that were worth preserving be sent to Trinity College Library. Watson had always been fond of Trinity College, and so this seemed to be a natural place to deposit Watson's papers. So during Rankin's sorting through these papers over a period of 3 years, he uncovered batches of Ramanujan's material. So in particular, in December of 1968, he sent Trinity College Library a large amount of results of Ramanujan. But he never told anyone. So the papers of Ramanujan then were just sitting in the library at Trinity College for about 7.5 years before then Andrews rediscovered, you might say, the papers of Ramanujan. Rankin, by the way, didn't like the fact that Andrews called these papers the Lost Notebook. He said it really wasn't a notebook. It was just a sheaf of 138 pages, and it wasn't lost. I mean, he knew about it, and I guess the only other people knew about it were Mrs. Watson and J.M. Whittaker's, a son of E.T. Whittaker, and of course the librarians. Let me just indicate a few topics from the Lost Notebook. So there are a lot of results on Q series, even more so, many more so than in the notebooks. So often a theorem on Q series will have an analog in the theory of hypergeometric series. So let me just briefly indicate why this is the case. So if you replace a by q to the a, and take q to the a over q, or q to the aq, and divide by 1 minus q to the n, and write that or quotient in this way, and just apply L'Hopital's rule to each of these n quotients, you get then in the limit the rising factorial notation. So you can't really do this and get exactly an analog or Q analog of a hypergeometric function, or conversely, but often one theorem, series evaluation, or identity points to another one in the concomitant field. So here is actually a Q analog of the binomial theorem. So in the lost notebook, there are a lot of results on false theta functions and partial theta functions. So a false theta function is a theta function, but you change the sign of infinitely many terms. So here is a false theta function. This is really the function psi of q that I mentioned earlier, involving the triangular numbers. So the -1 to the n is inserted. So this is a false theta function. And a partial theta function is like a theta function, but we eliminate some of the terms, usually half of the terms. So this would be a partial theta function on the left. And I'm actually giving you an identity for this partial theta function in the lost notebook. So it's remarkable that these functions, false theta functions and partial theta functions, have rather extensive theories. You see, they do not have Jacobi triple product identity representations. They don't have any product representations. So you're really at a disadvantage, so to speak, in regard to developing a theory, because they don't have these product representations. But Ramanujan had many results in the lost notebook on false theta functions and partial theta functions. The main topic of the lost notebook are Mach theta functions. So let me just quote a portion of the letter that Ramanujan wrote to Hardy from India, the last letter. So what he's doing is examining a Q series as t tends to 0 when we write q as e to the minus t. Okay, so here is one result which he gives. So this is an asymptotic formula as t tends to 0 or as q tends to 1. Okay, the little o1 means that the following: if a function is little o1 as x approaches a, if the limit of x approaches a of f of x is equal to 0. So in other words, the remainder here tends to 0 as q tends to 1 or t tends to 0. So this is actually the reciprocal of a theta function. It's actually the reciprocal of f of minus q, which I gave you early. Then he asks, is the converse true? Suppose we have a q series that exhibits an asymptotic behavior like we have above. Okay, must the function actually be a theta function? Plus some, say, easy, he calls it a trivial result or function. In other words, an easily identifiable function. Ramanujan says not necessarily so. When it is not so, I call this a Mach theta function. So these have been the subject of an enormous amount of research in the last 3 decades. There is a theory of Mach modular forms that has arisen, which indicates where Mach theta functions fit into a much broader theory. So there are many beautiful results on Mach theta functions in these notes. This is another famous result of Ramanujan, which I'm going to give you. This is a sub n or a q sub n defined now for every integer n. So if you take n to be a positive integer, this actually reduces by just cancellation to to AQ sum n as I originally defined it. So the reason I give this definition is that I want to quote very famous result is 1 psi 1 summation. So this in some sense is an analog of the Q binomial theorem, but now we have these more general Q products in the summands, and we're going from minus infinity to infinity. So this is a very useful result, this Ramanujan 1 psi 1 summation. A lot of results in Eisenstein series in the Lost Notebook. So Ramanujan Q is actually what we call E4 of tau, where Q is e to the 2 pi I tau, and E6 is really R of Q, or R of Q is E6. So these, I'm using the notation in here, modular forms. Yeah. So also published with Ramanujan's Lost Notebook. The Lost Notebook was not published until 1988. But with the Lost Notebook were published all these other manuscripts and fragments of manuscripts that Dewsbury sent to Hardy in 1923. So in particular, there are 7 manuscripts for which we generally do not have the original manuscripts of Ramanujan. They are in the handwriting of Watson. So you might ask, then, are there other manuscripts of Ramanujan that have been lost because Watson didn't actually make his own personal copies of the manuscripts? This one involving P of n and Ramanujan's tau function is the most famous of the manuscripts and has inspired an enormous amount of work in the last few decades. So I'd like to tell you in detail about one formula from a fragment in Ramanujan's Lost Notebook. So it's not really in the Lost Notebook, but one of these loose papers that were published with the Lost Notebook. So I'm going to go into this problem in detail in order to get to this formula and help you appreciate what the formula is. So we let R2 of n denote the number of representations of a positive integer n as a sum of 2 squares. So we are going back a little bit then to the first entry from Ramanujan's first letter that I mentioned. But now, instead of just looking at those integers which are a sum of 2 squares, which we would then count once, here we're counting all of the representations by R2 of n. Excuse me. And then we count different signs as yielding distinct representations. So for example, you can write 5 as plus or minus 2 squared plus or minus 1 squared. And then you can reverse the order of the summands. So R2 of 5 is equal to 8. Now, each of these representations can be associated with a lattice point in the plane. So for example, if you take 5 as minus 2 squared plus 1 squared, you associate this with the lattice point minus 2, 1. Now, each lattice point can be associated with a unit square. So there are 4 possibilities, but we should be consistent. So we're going to take the unit square for which the lattice point is in the southwest corner. Yeah. Okay, so what I've done in this picture here is to take all of the lattice points in the circle of radius square root x, and then colored red the associated square corresponding to the lattice points. Yeah. So then what we are getting here then, or what we have, is the sum of all of R2 of n taken over all n less than or equal to x in this circle of radius square root x. So here the prime means that if x is an integer, we only count half of the terms. And the reason we do this is because when we study the sum analytically, this is the sum with the prime that naturally arises. Okay, so you see then that if you look back at the number of these lattice points, numerically this is equal to the sum of the areas of these squares. And that is about equal to the area of the circle, namely pi x. So this is a good approximation, but of course this is not exact. There's going to be an error term, p of x, we'll say. So the question is, what is this error term, p of x? Okay, well, Gauss was the first person to look at this, and he said, well, this sum is all these points are in a circle of radius square root x plus square root 2. And then if you take a circle of radius square root x minus square root 2, this will be the interior will be all red. So from these two inequalities, we get that r of x is pi x. And then the error term is big O of square root of x. So just in case you're not familiar with the big O notation, we say that f of x is big O of g of x as x tends to infinity if there are constants c and x0 such that for all x greater than or equal to x0, we have this inequality. So Hardy worked on this problem of finding estimates for the error term. And in a famous problem that he wrote in 1915, he gives a formula for the error term, namely as this infinite series of Bessel functions. And he says, the form of this equation was suggested to me by Mr. S. Ramanujan, to whom I had communicated the analogous formula for d of 1 plus d of 2 up to d of n, where d of n is the number of divisors of n. Well, I've always felt that this is a very strange way of stating this. So if it was suggested by Mr. Ramanujan, it must be that he really had the formula, because you would never sort of guess this formula without actually having a proof of the formula. So often what one does to get an estimate for this error term is to use an asymptotic formula for the Bessel functions and then estimate the series that you get. So Sierpinski actually did this earlier. He didn't actually have the identity. He showed that the error term is big O of x to the 1/3 as x tends to infinity. And there have been many improvements upon this in the last century, but the best result we have is still above 3/10. I won't say anything more here. And now I'm going to tell you about an elementary identity. So in elementary courses of number theory, this representation for R2 of n is often proved. So I'm going to write these summands in a different way in terms of the sign function. Now I'm thinking of every divisor of n as being of the product dj. So in other words, we're summing all over products dj less than or equal to x in this sum. And if you sum on j first, that's just the square brackets of x over d, where this is the greatest integer function. So we have this rather elementary representation of our sum function here. Now let me state Ramanujan's claim, one of two claims from this fragment. So we're going to use sort of Ramanujan's notation, or we're going to define f of x as being the square brackets function, or x minus a half of x as an integer. Now, so this is about this. This is really the same thing as putting a prime on the sum. So this is the formula, the first of two formulas from this fragment published with the Lost Notebook. So I want to convince you that this is really an interesting formula. So we have a double series of Bessel functions here. So first, let me give you a little historical background. This was first proved in a paper I wrote with my former student Sun Kim and my colleague Alexandra Zaharescu in 2013. Here is a picture of my colleague Zaharescu. And here is a photograph of Sun Kim and myself that was taken when she got her PhD. I might add that I've been It's been a privilege of mine to co-author papers with several mathematicians. I've co-authored more with Alexandru than I have with any other mathematician. And I've co-authored more papers with my former student Sun Kim than I have with any other of my former students. Well, now I'm taking you to a version of myself and Zararescu only. We proved this in 2006. So you might ask, well, why did I say we first proved the result in 2013 if Zararescu and I proved the result in 2006? Well, if you very carefully look at the identity, I've reversed the sum here. So it turns out it was easier to prove the identity if we reversed the order of summation. So Ramanujan's identity, again, would be summing on n first. So the proof that we gave of Ramanujan's result, the way he stated the result, is entirely different from the proof that we gave earlier. We couldn't use anything from our earlier proof in our later proof. Okay, so why is this result interesting? Well, the sum, note on the left-hand side, is a finite sum. And if you take theta to be a quarter, you actually get the elementary formula for the sum of R2 of n that I gave you earlier. So again, the case theta equals a quarter gives us the elementary representation on the left-hand side. So there's actually a third version of the formula. You can interpret the sum with the product mn tending to infinity rather than an iterated sum. And so we proved the theorem in this way as well. So the big question is, can we use this extra parameter theta to attack the famous circle problem of Gauss? So often in analytic number theory, if you can introduce another parameter, this gives you something more to work with. And you could maybe prove a theorem that you want to prove or conjecture that you want to prove that you wouldn't otherwise be able to prove without this parameter. So I thought about this for over a decade, and I have no answer to this. In other words, I have not been able to use this extra parameter to attack the circle problem. And then note one more thing, what we have here is the left side is an elementary function of theta, but the right side is a Fourier expansion, or similar to a Fourier expansion, and the Bessel functions are the same ones that appear in the Ramanujan-Hardy formula that I gave you earlier. Yeah. Okay, so this formula of Ramanujan is very interesting for several reasons, and we don't know if Ramanujan derived this formula to attack the circle problem or not. Let me go back to Hardy's paper again. So in this paper, he gives this beautiful formula, and he says that Ramanujan gave him this formula. It's really beautiful because if you take the left side and change the roles, interchange the roles of A and B, Ramanujan is saying you get this right side. So it's certainly very rare in mathematics that you can invert the roles of a couple of variables and get the same thing. So it's really a beautiful result. Yeah. So the formula that I gave you earlier and this formula of Ramanujan are not found anywhere in Ramanujan's work. So it's natural to ask the question, how many results of Ramanujan that he communicated to Hardy may have been lost? Of course, we have no idea about that. Yeah. Now, if we take this formula and differentiate it with respect to B, let A tend to 0, make a change of variable here, and then you can use analytic continuation and get a result for the real part of S greater than 0. You get this formula. So in fact, this is actually what Hardy used to get the famous results that I'll tell you about next. Now, I should say that Hardy also had another proof of this result. But if I were Hardy, I would have listed Ramanujan as a co-author of this paper. I think sort of the practice of using co-authors or having co-authors has changed over the years. In Hardy's day, I think it was much stricter than what we have today. So in my opinion, Ramanujan should have been, because of these two results, co-author with Hardy of this paper. So Hardy proved in this paper that the error term is omega plus or minus of x to the 1/4. Okay, let me explain this notation. For the plus sign, this means there is a positive constant C1 and some sequence tending to infinity, such that on this sequence, the error term is bigger than constant C1 times xn to the 1/4. And then for the minus sign, what this indicates is there's another constant C2 and another sequence tending to infinity, for which the error term is less than minus C2 times the sequence terms to the 1/4. So what this implies is that the error term is at least 1/4. In fact, it has to be slightly bigger than 1/4. So this is the conjecture that has been made for Gauss's circle problem. The error term is big O of x to the 1/4 plus epsilon for every epsilon greater than 0 as x tends to infinity. So it's one of the most famous problems in number theory, and we're far from solving this problem. So again, the question is, did Ramanujan have an idea for solving this problem? He obviously was interested in sums of squares. So there's another formula from this fragment involving the divisor function, d of n. So d of n is the number of positive divisors of n. So for example, d of 6 is 4, 1, 2, 3, 6 being the divisors of 4. And then Ramanujan has a formula for this sum d of n. I'm not giving you the formula because it involves other Bessel functions. And there's an error term here. So the question is, what's the order of the error term? And Dirichlet showed the error term is big O of square root of x. So the Dirichlet divisor problem asks for the correct order of magnitude of this error term as x tends to infinity. So generally, if we have an estimate for the error term for the divisor problem, we have a similar result for the circle problem and conversely. Now, so again, we think that Ramanujan derived his identity, which I'm not giving you, in order to attack this famous problem of Dirichlet. So this formula of Ramanujan, which again I haven't given you, was actually the last result from Ramanujan's lost notebook that remained to be proved. In the work that Andrews and I had done on the lost notebook, for me a period of a little over 20 years, and for Andrews a period of around 40 years. So we actually proved this identity last year. This was the last identity to be proved, and this is the paper in which we actually proved the identity. So we chose the Proceedings of the London Mathematical Society because Watson had proved, or had made his famous paper, wrote his famous paper for the Journal of the London Mathematical Society. So here's a picture of Zarescu. He's now grown a beard with his PhD student, Junxian Li. I'll tell you about one more problem from the lost notebook. So Ramanujan was very fond of evaluating infinite series, the Bessel functions. So there are many classical values for the evaluation of the Bessel function. Excuse me, I'm sorry, I said Bessel functions. I meant theta functions, of course. So remember that phi of q is the sum of q to the n squared in running from minus infinity to infinity. So here is one classical value. And you can replace the power here by 2, or really any power of 2, and carry through the evaluations. But for other values, other than these classical values, the problem is much more difficult. And Ramanujan, in his lost notebook, has several new values of for this theta function phi. So yeah, here is the value of phi of e to the minus 7 pi. The values naturally come with the value of phi of e to the minus pi. So that's why we state the theorem in this form. Well, on page 206 in the lost notebook, Ramanujan writes, for example. But note that he doesn't tell us what these quantities are. So in some sense, this is the last problem, but there are other results for which we cannot make, not very many results, but for which we cannot make a proper interpretation. So I've said here, identification of the missing terms is yet to be made. I think very recently an identification has been made, but the author is reluctant to tell us what they are. He did tell me what these missing terms are, but he wants to go through the proof, make sure that indeed he has a bona fide proof of this result. Then, so there are a couple results like this for which the statements are incomplete that Ramanujan gave. So I think this is all I'll say about Ramanujan's notebooks and Lost Notebook. Let me just conclude my talk with a few sentences from Freeman Dyson. So in 1987, we held a meeting at the University of Illinois to celebrate the centenary of Ramanujan's birth. So let me quote a couple of sentences from Freeman Dyson's talk at this meeting. I am grateful to the organizer of this conference for bringing me here and giving me a chance to enjoy all the new flowers that have been growing in recent years in Ramanujan's garden. And then he concluded this talk by saying, whenever I am angry or depressed, I pull down the collected papers from the shelf, and I might add the notebooks in the Lost Notebook, and take a quiet stroll through Ramanujan's garden. I recommend this therapy to all of you who suffer headaches or jangled nerves, perhaps from COVID-19. And Ramanujan's papers are not only a good therapy for headaches, they also are full of beautiful ideas which may help you do more interesting mathematics. So indeed, these sentences of Freeman Dyson are greatly true. So thank you for giving me the privilege of speaking with you about Ramanujan and his mathematics. If there's time, I'll be glad to answer any questions you might have. I'll stop sharing the screen.
Good evening, Professor. I would like to know from you, Professor.
Yes, can you see me here?
Yeah.
Okay.
Yes, sir. Can you hear me?
Yes, yes.
Please, sir.
Mm-hmm.
Yeah. I'd like to know from you about your work on topics with relation to applications, and that's your favorite area in other fields? Favorite application in other fields? Can you share?
Well, I actually have not worked on applications themselves, just because I spend my time working so much on what Ramanujan actually gave.
Yeah.
In fact, a lot of the proofs that we have are certainly not what Ramanujan had. In particular, for some of the proofs, we have just verifications. In other words, they really aren't natural proofs. Ramanujan gives us the formula, but then, we are greatly helped by the formula he gives us. And then we know the formula, so maybe we can then find our own proof, but it's not the natural proof. So for a lot of results we have, we think our proofs are similar to what Ramanujan had. But there are other proofs that we think are not close to Ramanujan's proofs. So this is what I've been concentrating on. And I've also been concentrating on using Ramanujan's ideas to get further results. So for example, in the last result that I talked about on the circle problem, we have found that we can prove several other theorems of this type. So for example, for the circle problem, we have a sine function on the left-hand side. We can now derive identities involving the product of any number of sines, and also a sine times a cosine, for example, or two cosines. And we've also found proofs for other kinds of divisor functions, that is, identities not only for the divisor function d of n, but for other kinds of divisor functions. So I'm afraid this is what I spend my time on now. So there have been applications, which I really don't know, to string theory and to black holes and to communications. There is a professor at Caltech, I'm sorry I don't remember his name, who has used Ramanujan sums a lot in his work in communication theory. And for black holes in string theory, the Mach modular forms, this generalization of a Mach theta function that was originally due to Sanders Swagers, these have been used in these sophisticated areas in physics. And I've seen a few other applications from time to time, but these are probably the most famous that we have now, but I have not been working on these applications.
Thank you very much, sir.
Yeah. Any other questions?
No questions.
Okay.
Thank you, Professor. Yeah, it's really a pleasure for us to see those memorable photographs and notebooks of Ramanujan's lifetime. So, Ramanujan's work has been a source of inspiration for generations of mathematicians. Pi Mathematics Association is extremely grateful to you, Professor, for your effort and contributions you have made for the advancement of Ramanujan mathematics. Thank you very much, sir. Now, I request Mr. Kalyan Kumar, member of Pi Mathematics Association, to thank our eminent speaker. Please, sir.
So, on behalf of Pi Math,
Kalyan Kumar, sir?
Yeah, please go ahead with the question.
Yeah, please.
Yeah, let me add one more thing. Yeah, the photographs I've taken, I have several photographs. Many I took of Ramanujan's home and the interior of Ramanujan's home. And our Balasubramanian accompanied me on this trip, and I'm very grateful to him for accompanying me. And I would like to take further pictures of Ramanujan's home in the notebooks in Chennai. The pictures I have were taken some time ago, and I would like to take these again, some of these pictures again, with a better camera. So on my next trip to Chennai, I hope to get some further pictures connected with Ramanujan. I see there's a question here. Suppose Ramanujan would not have died at the age of 33. Actually, it was 32. How much mathematics would stand now? No. I might add that there is a fair amount of mathematics that has been lost. So from Ramanujan's first letter to Hardy, at least 3 pages have been lost. From his second letter, at least 1 page has been lost. From his last letter to Hardy, at least 1 page has been lost. We have 11 letters that Ramanujan wrote to Hardy from nursing homes, and we know that some other letters have been lost. So with this question, when does it end? It will never end, I think. And Ramanujan's mathematics is still, well, I shouldn't say still, it is the foundation of much research that is still going on. And I think the influence is growing with every year. More and more research connected with Ramanujan's discoveries that is being conducted.
On behalf of Pi Mathematics Association, I would like to sincerely thank Professor Bruce Berndt for delivering us this lecture today. So today we had the privilege of listening to a lecture from a mathematician who had devoted his entire life towards the research and work and notebooks of Ramanujan. We assure you, sir, we would take this lecture as a starting point, and we will spend more time and research to grasp the concepts. And we really appreciate your time and effort you have put in preparing the materials. And so I sincerely request all the students here to make maximum use of the materials provided and enhance their knowledge. On behalf of our association, I thank you one more time, sir, for um, providing us with this lecture and providing such detailed topics about Ramanujan's works and elaborating some topics like the circle method and so on. I sincerely thank you, sir.
Well, thank you for the invitation. I always enjoy talking about Ramanujan and his mathematics.
Sure, sir. Sir, honor.
It's a great pleasure and privilege for us to hear from you, sir.
Mhm.